Welcome to this video, which is the first of a series of 4 parts from Vantage on dimming LEDs. Our objectives are to help Vantage installers and specifiers feel comfortable with their choices when matching our dimming technologies with LED sources they desire to control, and to take full advantage of the capabilities our technologies deliver. This first part will touch upon fundamentals of dimming, which is foundational to all subsequent parts of the series. Let's begin by examining how a typical dimmer works. By altering the amount of power delivered to a light source, a dimmer directly affects the level of light output from that source. The more power delivered, the higher the light output. The less power delivered, the lower the light output. The two extremes of light output range are, of course, achievable by a simple switch. With a simple switch, we either turn the light on, meaning we close the circuit, delivering full power to achieve the full light output capability of the lighting load, or we turn the light off, meaning we open the circuit, cutting off power from the lighting load and getting no light output in return. While this explanation is obvious and simple, the concept is actually foundational to the understanding of how typical dimmers work. In order to achieve a light level from our given lighting load that is somewhere between fully bright and fully off, what the dimmer actually is doing is switching power on and off at a high rate of switching, thereby reducing the power delivered to the lighting load and resulting in a lower light output. The frequency of the switching is high enough that our eye cannot see it. The very nature of the power delivered by the electric company makes this feasible. This graphic represents a single cycle of the delivered sinusoidal voltage signal. This cycle repeats 60 times every second. Using a simple light switch and turning that switch on, we would be delivering this voltage to the lighting load throughout the entire cycle. As a result, current would flow through the lighting load. The product of the voltage applied and the resulting current through the lighting load would determine the power delivered to the lighting load. To reduce the light level output again, we need to reduce the amount of power that's delivered, and we'll do so by switching twice, off and on, during each cycle. Using power electronics such as a triac, we can turn the voltage off where the sine wave crosses the zero line. Then we leave it off for a certain delay, then back on in order to deliver some power, reduced power, to the load. And we do that again on the negative side. The longer the delay before turning on, the less power we'll be delivering and the lower the light level of the light source. So this then would be the modified waveform coming out of the forward phase dimmer. We will now demonstrate in real time the operation of a typical dimmer. Our setup is this. The output of the dimmer is connected to the light you see here. And additionally, an oscilloscope is displaying the dimmer output voltage. We will now initiate a gradual fade off. Watch the change in the voltage waveform as the light fades. Notice that as the delay time increases, the light output decreases because less power is being applied. So this is how a standard dimmer works. A dimmer with the output characteristics demonstrated here is known by many names, including standard dimmer, household dimmer, incandescent dimmer, triac dimmer, magnetic dimmer, forward phase dimmer, leading edge dimmer. We'll refer to this throughout the remainder of the series as a forward phase dimmer. Vantage offers several varieties of forward phase dimmers, as seen now. The standard dimming module, the DIN standard dimming station, the standard power station, the scene point dimmer, the accent point lamp dimmer, the RFLC dimmer. Keep in mind that this dimmer was developed for dimming conventional light sources, particularly incandescent lamps. These light sources are resistive in nature and they don't care about the shape of the wave applied. They will react to how much power is delivered to them regardless of the waveform. When the lamp is low voltage, and a transformer is used to convert the line voltage to 12 volts, for example, to apply to that lamp, then in addition to the lamp itself, some complexity is introduced by the transformer. Now, conventional wire-wound or magnetic transformers are compatible with this type of dimming, or forward phase dimming, so long as certain factors are implemented in the dimmer. For example, the power delivered during the positive half of the cycle must equal the power delivered in the negative cycle so that any DC component of the power delivered is within tolerance of transformers. An out-of-tolerance DC component would cause the transformer to saturate, leading potentially to its failure. So the difference between an incandescent rated dimmer and a magnetic rated dimmer is the latter's ability to perform without detriment to the transformer. They are both forward phase dimmers. All Vantage forward phase dimmers are magnetic rated. At one point in the history of light source development, the electronic transformer was introduced with a very different set of characteristics from those of a magnetic transformer. One key difference is that it is not at all compatible with a sudden voltage rise that occurs twice during each cycle in the scenario that we've just looked at. So there's a compatibility issue between the electronic transformer and the standard dimmer. You cannot use the two together. The solution to dimming electronic transformers is to swap the sequence of power delivery to the lighting load each half cycle. Instead of opening the switch at the beginning of the cycle, the switch is closed, and at that point the power is delivered for a time. Then after a predetermined delay, the voltage is turned off and power is no longer delivered for the remainder of the half cycle. In this way, no sudden voltage rises occur, so it works with the electronic transformer. This then is the waveform from an electronic transformer compatible dimmer. We will now demonstrate this backward waveform dimming method live on an oscilloscope, as we did before for a forward phase dimmer. I will now initiate a gradual fade off so you can see how the power delivered decreases while the light output decreases. Dimmers that produce this backward waveform are known by the following terms: ELV, or electronic low voltage dimmer, simply electronic dimmer, reverse phase dimmer, or trailing edge dimmer. We will refer to these from here on out as reverse phase dimmers. Vantage also offers an assortment of reverse phase dimmers, as seen here. The electronic dimmer module, the DIN electronic dimmer station, the electronic power station. Again, the incandescent light source without a transformer doesn't care about the waveform. So we can dim the line voltage incandescence with either forward phase or reverse phase dimmers. However, the following differences exist. The triac that is used to perform forward phase dimming cannot be operated in a reverse phase manner, and so different electronics are used for reverse phase dimming, typically a FET or an IGBT. These electronics are comparably more expensive than a triac, and their current ratings are typically lower. So if you use reverse phase dimming, you will pay a premium, and your load capacity will be somewhat lower compared to the forward phase dimmer. I should mention here that some electronic low voltage transformers have been modified specifically to be compatible with forward phase dimmers, such as the Lighttech LET75, as I hold here. The manufacturer of the ELV transformer must state that it is compatible with forward phase dimmers, or an electronic transformer should always be paired with a reverse phase dimmer. As these two introduced dimming methods share a common concept of switching power on and off during each half cycle, and because they're not the only means of dimming, we're going to classify them together and refer to them collectively as phase cut or phase control dimming. While phase control is still the primary dimming method, it is not the only method. Historically, there came the point when it became desirable to dim fluorescent light sources. But fluorescent lights don't typically respond well to phase control dimmers, so other methods of dimming became commercially available, all of which have carried forward in one form or another to LED dimming, so these are well worth our discussion. These other methods of dimming differ from phase control dimmers in that the dimmer is not actually directly modifying the power delivered to the lighting load. Rather, it's sending a signal, a control signal, to an intermediary electronic circuit known as a dimmable ballast in a fluorescent fixture, or as a dimmable driver in an LED fixture. The signal is used to communicate to what level the light output should be set, and the ballast or driver uses some mechanism beyond the scope of our discussion to achieve that lighting level. For this reason, I refer to dimmers that use these methods as indirect dimmers. Indirect dimmers are of two major types, analog and digital. We will discuss the analog indirect dimmers first. A light source, which includes indirect dimming capability, will be looking for a variable control signal separate from the power delivered. that power typically being switched on and off by the controlling dimmer in addition to the variable control signal. The first type of control signal we'll discuss is the variable low voltage output, sometimes referred to as 0 to 10 dimming. Such a device will react to a control signal that varies between 0 and 10 volts DC to regulate the light output. If the control signal received is 10 volts, the device causes the light output to go to its full on value. If the control signal received is 0 volts, the device causes the light output to go to its minimum or off value. A control signal value of 5 volts, being at the midpoint of the control signal range, would cause the light output, theoretically, to go to the 50% output level. A second method of analog indirect dimming is pulse width modulation, or PWM. In PWM, a constant voltage square wave, repeating square wave, is the control signal. Now, the percentage of the time that the voltage is on is actually the variable. We don't change the frequency, we don't change the voltage, we just change the duration that it is on. And that goes between 0 and 100%. Now, there is a standard that applies to dimming pulse width modulated controlled light sources. And that standard is actually opposite of what you might expect. Meaning that if I were to actually apply a 0% of the time the voltage, then the light output is actually going to be at 100% and reduce down linearly to 0% when we apply 100% of the time the voltage. Opposite of what you'd expect. Now, because it is opposite of what you'd expect, you do find from time to time manufacturers of PWM controlled light sources that don't comply and go more with what you would expect. With those light sources, if I apply a 0% of the time the voltage, then I will get 0 light output, and I will increase linearly up to 100% or full output when I get to 100% of the time that I'm applying voltage. Now, this non-compliant light source, if you're going to control that from within with Vantage, within Design Center, there's a box that says inverse that applies to this light load. And you are going to select that, meaning that it is non-standard. Hopefully, PWM dimming will become more clear as you see it live. We have the oscilloscope now attached to the output of our PWM dimmer. We will now initiate a slow fade off. Notice that as the percentage of time that the voltage is applied decreases, the light grows dimmer. Remember that this is non-standard, and we've selected in software the inverse option. Vantage offers 2 varieties of the LVOS, each of which is capable of delivering both 0 to 10 and PWM dimming. These 2 varieties are the panel-based LVOS and the DIN LVOS. A third and final method of analog indirect dimming uses a line voltage phase control waveform as a control signal. Such a device is characterized by a neutral conductor, a conductor for power switching, and a conductor for dimming control, so it's known as a 3-wire ballast or a 3-wire driver. While the power delivered to the light source is switched between the switch leg and neutral, in addition, a phase control signal is applied between the third conductor and neutral to signal the desired light output level. Finally, there is indirect digital dimming, wherein we'll send a series of bits according to a preset protocol to communicate commands and status updates over a 2-way serial communication port. 2 salient examples of this are DMX and DALI. While these technologies are mentioned to round out the discussion of dimming control, they fall outside of the scope of this series. I hope you'll find this discussion to be useful. Your understanding of the concepts presented here will aid in your understanding of the rest of the series. LED lights can be dimmed using any of the methods we've discussed today, and in upcoming videos we will further explore implications of these methods as they apply to LED lighting.